thank you all for being there. I'm going to be presenting the latest work of me and my colleague. Well, my name is Kasapis Spiridon. I am currently a postdoc at NASA Ames Research Center, but this is a project that was worked on during my summer internship at NASA Goddard Space Flight Center here at Maryland, in collaboration with all the people noted below, specifically Barbara J. Thompson, my advisor, and it is titled Turning Noise into Data, Characterization of the Van Allen Radiation Belt Using SDO Spikes Data. So without further ado, um, just a quick introduction about what the Solar Dynamics Observatory is. So the what is going to be referred as the SDO is a satellite developed by NASA's Goddard Space Flight Center. It is a flagship mission of NASA's Living with a Star program. It was launched in 2010 and is expected to remain operational until 2030. Is in a circular geosynchronous orbit inclined by 28.5 degrees in altitude of 35,000 kilometers. This orbit looks like this analemma, this figure 8, as seen from the ground station in White Sands, New Mexico. And oh, I'm sorry, this might happen a couple of times because I need to update this computer. But yes, this orbit allows the satellite to have continuous contact with the ground station in White Sand, and it also minimizes eclipses with the Earth. And obviously, most of you know a lot about the SDO, but its primary goal is to understand those solar variations that influence life on Earth and humanity's technological systems, aimed towards developing predictive capabilities of the solar activity. SDO is a satellite that has been very well used in our field. On board of the SDO, there is three instruments: the HMI, the EEV, and the AIA. In this research, we are going to be concentrated on the AIA, which you see right here. The AIA is an array of 4 telescopes. It takes high-resolution full disk images of the corona and the solar transition region up to 0.5 solar radii above the solar limb. It has 2 ultraviolet, 1 visible light band, and 7 extreme ultraviolet, the EUV. And in this research, we are going to be using the extreme ultraviolet bandwidths of the AIA instrument. So what is the AIA spike data? The SDO mission applies what we call the de-spiking algorithm, which essentially in every image that the AIA takes, in every wavelength, the SDO team removes what we call the brightened pixels of all these images. And this is being done because without it, the AIA image would be difficult to use for either machine learning or other solar observations. Kirk et al. Showed that 0.1% of these spikes are of solar origin. So we do know that these brightened pixels in each one of the AIA images, what we call these spikes, are not of solar origin. Very few of them actually are of solar origin. So therefore, it is easy to understand that these are of magnetospheric origin. So what we understand is that because of SDO's inclined geosynchronous orbit, which resides within the magnetic field of the Earth, the origin itself resides within the magnetic field of the Earth, these spiked pixels are essentially particles that reside there rather than photons that come from the sun. which is the rest of the image, not the spike pixel. So long story short, the goal of this research is to characterize the Van Allen radiation belt using these spikes, using this noise data in the AIA images that reside in the SDO's orbit. In this picture, you're going to see what an AIA image, where I'm pointing. Can I do this maybe? Pointer options, whatever. You can see my pointer. This is a typical AIA image, and this is what would be within 1 day the distribution of where this noise data, these spikes belong to. And as you can see, most of these spikes are out of the solar disk, where obviously we know that they cannot be of solar origin. They are of magnetospheric origin. Here on this on this plot on the right, you can see the 7 different wavelengths. So 94 angstrom, 335, yada yada. So for all different telescopes or wavelengths that the AIA can picture, the variation of the number of spikes that reside in each image for a complete year. Again, so there is a variation of how many spikes we can see in each image, depending on the day and time. We're going to discuss more about this. Here I kind of show you, whenever I refer to end spikes, this is good to know, I refer to this noise data that we see in the AIA images. I refer to these spiked pixels, these brightened pixels that we remove from the images. End spikes is the name of the header used by the SDO team. So here, what we see is for a typical 340 Armstrong image, we see that a typical one of these images contains like 50,000 spiked pixels. So 0.3% of all the pixels are going to be the spike pixels that we remove. Here we can see the distribution of how many spikes are residing in each image, and if we take the log, we can really see, because obviously most of them are around this 50K range. As one is to essentially zoom in, we take the logarithm, and we can see this very nice distribution of how many these very nice canonical or rather Gaussian distribution of how many spikes reside in each image. So you're going to notice this distribution too. If I do have time, I'm going to make a note about it. But in this research, we are mostly concentrated on this big distribution rather than this one. And I'm going to note why in a bit in this presentation. The number of spikes, as I say here, can be in the millions, so it can be much higher during periods of enhanced particle flux. So obviously particles are going to be hitting our instrument much more if there is enhanced flux. And over the course of 12 years of the SDO operation, there have been over 200 million AIA images, so 6 trillion pixel hits. So what is considered as noise and is taken out of the image is a lot of data that we thought with Barbara Thompson and our rest of the colleagues here at NASA Goddard that it might be a useful data product indeed. And I'm going to show why in my next slides. So the first thing that we did is take this distribution of the number of spikes detected in all these images and wavelengths and see whether they correlate at all with the geomagnetic indices. Geomagnetic indices that we test in these in this study is SIM-H, a proxy of the axially symmetric magnetic field disturbance at low and middle latitudes on the Earth's surface. This is measured in nanotesla. And then the K-index products, which is the KP and the AP index. And here we can see, as we saw previously, the how the number of spikes changes throughout time for an entire year. This is specifically the year of 2019. So where I'm pointing, you can see the 7 wavelengths of the AIA, and the fluctuation of the number of spikes detected, number of noise essentially detected at the AIA images. And we can see that it kind of correlates. Here I zoom in for the month of February. It does kind of correlate with all these indices. When there is high noise in the AIA image, so the high number of end spikes, we can see that the AP index, increases similar to the KP. The inverse obviously happens for the SIM-H. This is the nature of the SIM-H geomagnetic index. So this is the results when we correlate the number of spikes with the geomagnetic indices. We can see that we can get up to a 0.346. Oh no, again. It appears a correlation of 0.346. This is not a great correlation, but still shows that it's not completely random. There's some correlation. Similarly, for the Spearman correlation for the AP and the SIM-H index. So there is something going on there. So let's do a parenthesis to all that I talked to you about right now, and let's talk a bit about the GOES 14 satellite. And I'm gonna I'm gonna note why the GOES 14 satellite was important for this research. So GOES 14 is a weather satellite. It's part of the NOAA GOES system. It was launched in 2019 on 105 degrees west longitude, kind of on the same, really on the same altitude as the SDO, and pretty, in a kind of similar, not similar orbit, but very close to the longitude of SDO, as I note here, which is going to be important, and I'm going to show why in the next slide. GOES 14 includes a lot of instruments, 9 different, to be precise. In our research, we're going to be using the data of these 3 specific research instruments. I'm sorry. So the MAGD, which is the magnetospheric electron detector, detects like an instrument that detects electrons. The MAGPD, the equivalent but for protons, and the EPAD, the energetic proton, electron, and alpha detector on board of GOES 14, the GOES 14 satellite. There's a nice picture of the GOES being launched at Cape Canaveral. Please feel free to interrupt me if anything.
Yeah, 5 minutes.
Thank you so much. So the why we are using the GOES 14 satellite, this is a mistake. It's not GOES 15, it's GOES 14. The reason why we are using the GOES 14 satellite is because twice a day we noticed that the SDO and the GOES 14 satellite come into like very close. There's these 2 conjunction points that come to very close proximity with each other. They essentially study the same space in the magnetosphere, both satellites, SDO and GOES 14, as we can see here in red. These are the conjunction points, which are, as I note here, as close as 1,600 kilometers from each other. This is very close for obviously space. And so on the rest slides, what you're going to see is 3 different types of comparisons. We're going to be comparing the GOES 14 data with the SDO spike, like noise data, in three different ways. In their full orbit, right? So everywhere in both the orbits that you can see here. In the conjunction points, so only at the times and space where the satellites are close to each other, so the red points, and then obviously the non-conjunction points. So whatever is out of these conjunction points. This is really how we pick the equator data. So we define like a threshold of like 2 times 10 to the 6 meters from the equator. So really what I have here marked as red. And this is, the data that we seclude for our, what we call later on the equator or conjunction point comparison. So here you can see that for all these different energy bands of the flux that is the electron flux that is detected by GOES 14, uh, like there is quite a correspondence with the number of spikes detected by the SDO. It is pretty obvious here. Uh, but we also are going to concentrate on the equator data because we believe that there is where we're going to have a better correlation just because the satellites again study the same space. Come on. So the results, the first set of results is the MAG-ED electrons. So electrons that range from 40 kiloelectrovolts to 475 kiloelectrovolts in these five different bands. We can see that our the noise data from the SDO satellite has a very high Spearman correlation in the order of 0.729 with these MAGID electrons on the equator. This is on the equator. We can see that in the non-equator areas of SDO and GOES 14, obviously this correlation decreases quite significantly. Obviously, in the full orbit too, but still there is a correlation, which is very interesting. So very high correlation on the equator. This is an extremely good Spearman correlation for the type of data that we're discussing. And yes, let's see. So if we take all the spikes detected from, in this case, the 304 Armstrong instrument on board of AIA, so part of AIA, we can see that we get a Spearman correlation of 0.78, or I'm sorry, this would be a Pearson correlation of 0.78 and a Spearman correlation of 0.75. And this is really what the data looks like. On the x-axis, we have the noise data from SDO, the SDO spikes, or the logarithm of it. And on the y-axis is the GOES 14 electrons, the electrons that are observed by the SDO. And we can see that we can really see this x equals y kind of um, distribution or relationship between these two data sets, essentially, or data and noise. Here we also do some fitting of some lines, weighted least squares, etc. So this is the equator data, very good correlation within the equator. This is what we visualize. This is for the old data. We can see that still there is some correlation, but obviously the spread um, around these best fit lines is much bigger, which is something that we expected by seeing the numbers previous slide. But really, these images show us that the SDO spikes, knowing the number of spikes or noise data that is seen and detected on the AIA images could very well be a good proxy measurement for the ghost 14 electrons. So if we knew that there's 4.5 in the order of the logarithm 4.5 SDO spikes, we could go up here in the best fit line and say, hey, probably the ghost 14 electron instrument would read this many, this much electron flux. So this is great. We extend this same analysis to the EPAD electrons. The difference between the MAG-ED and the EPAD instrument is that the EPAD has 3 channels that detects higher electron flux in the order of 0.882 and 4 mega electrovolts, whereas the MAG-ED was in the order of up to 0.5 mega electrovolts. And in this case too, we can see that although we have like a lower correlation, especially in the equator, compared to the MAG-ED electrons, I want to remind you that the MAG-ED correlation was at the order of 0.7. Here we have in the order of 0.534, and obviously a decreased number for the non-equator data where the satellites are not close to each other. But still, even for high energy electrons, there is significant correlation between the SDO noise data and the electrons detected by GOES 14, which is great. And here I need to note that these numbers, what I show you, is for the period of December 2017 to February 2022. So this 3-year period where the SDO and the GOES 14 satellites worked, or we have data, uninterrupted data, let's say, from both the GOES 14 and the SDO, which is again these 3 years.
Time's up. Sorry. Yeah, please, can you
Awesome.
go to the
Yes,
comments?
I will wrap up. We did the same thing for like protons of the GOES 14. This is the results. We noticed that also there is a correlation with protons, much lower correlation with protons from the MAG-PD proton instrument on board of GOES. We did an analysis to show that protons is probably not the main source of these spikes. It's really electrons, and we did this by comparing SCP events with the number of spikes. And this is my last slide, the conclusion. So what we show in this research is that, well, first of all, SDO goes out of the ecliptic and can be used to measure electron densities on unique orbits, thus helping us characterize the radiation belt in areas where other satellites like GOES cannot reach because of this inclined geosynchronous orbit that SDO provides us. Most GOES satellites have been decommissioned, whereas SDO will be operational until 2030. Therefore, the SDO, what this analysis can provide these values that we can get from GOES 14 satellite. And therefore, long story short, we create a new data set which can be used for machine learning or for the characterization of the Van radiation belt. We create a new data set with proxy measurements from electrons of the outer radiation belt within and out of the equator, turning the radiation belt characterization into a 3D structure, but not only that, turning SDO also into a Van Allen radiation belt characterization satellite. So this is it. Thank you very much for your attention, and I'm sorry for taking an extra minute. Please, if any questions.
Thank you very much. Any questions in the audience for Spiridon? Yes, Robert.
Hello, thank you for the interesting talk. I have maybe like 2 related questions. So the first one is, so this looks like it's related to the electrons that that hit on the sensor, basically. Is this kind of what we expect from the sensor, and also in terms of the sensitivity of the sensor, that we observe the SEPs in that way?
Yes, so great question. Yes, so we one of the authors of the paper. The paper is published like a couple of like a month ago. Was published as Space Weather, AGU Space Weather. There is a lot of information about what you just asked in the paper, but so the principal investigator of the AIA instrument is the co-author of the paper, and one of the big questions that he was posing and we were posing to him too is whether we could look into the physics of how the instrument itself is built and whether those electrons could penetrate the shielding of the instrument in order to induce this noise. We do not have a clear answer in terms of physics, but it seems that we do have a clear answer in terms of data. So our data, comparing the data, the electron density within the radiation belts and what the instrument reads as noise, it seems that there is very high correlation. So this leads us to be thinking that yes, the electrons do penetrate the instrument itself. But this is something that is, kind of scraped on the paper, but not really discussed. So we do not discuss the physics itself of how the electrons or the protons penetrate the AIA instrument. This would be actually a very interesting study for us or for Lockheed Martin, who runs the AIA instrument.
Okay, thank you. And maybe on the second question, I was wondering if there is also a correlation if you would consider a certain time delay. So for example, if you would consider like the photons that lead to a spike, you would have a certain delay between the photon spikes and the SEPs that are arriving. So in the range of like a couple of minutes. Have you also considered like shifts in time and to verify or to estimate the correlation with individual time delays?
That's a great question. Let me clear up one thing. So photons are what we would expect to see in the AIA images. The spikes are most likely protons or electrons. As I said, they're not of solar origin, therefore they're not photons. So whatever I discuss here as spikes is these spikes are a product of either protons or electrons, right? So I just want to make this clear. Now, to answer your question, we see here this table really summarizes very well the outcomes of this research. There's very high correlation with low energy electrons, medium correlation with high energy electrons, and medium correlation with protons seen by the GOES satellite. Now, why is this important? We do believe, we are not certain about it. This is the very first research that has been done in this issue, but we here in the SCP comparison can see that the number of spikes is probably, or the spikes themselves are probably not of proton origin, but of electron origin. So let's take, for example, this SCP. These are the three most intense SCP events from 2010 to 2020, as seen by both GOES and SDO. And we can see here in yellow, although we have a very high proton flux during that SCP event, we do not have such an increase in the number of spikes in this case. Similar for this SCP event. Now here you're going to see that this is interesting because although in these two SCPs there is no this correlation whatsoever, here there is some correlation. Why does this happen? We believe that there is correlation with the protons, not because the spikes detected in the AIA are protons themselves, but because the intensity of the protons depends on the intensity of the electrons within the radiation belt, which is what we see in the AIA images. So when it comes to SCP events, I do not think, this is not clear, but I do not think as of now that uh, the AIA spike data would be a good proxy measurement straight away, because I believe that it is not detecting protons, but it's detecting electrons that are correlated with protons. And the last thing that I want to point out when it comes to the time delay that you noted, yes, indeed, within the paper, we do, in our analysis, for the correlation between SDO spikes and the geomagnetic parameters, we do an analysis on the time shift. And we do notice an quite insignificant time shift of like around 3 hours. But this is something indeed that we should look more into the future. Again, this is the very first study that is being done in this noise data.
Thank you very much.
Yeah, thank you.
Any more questions in the audience? I don't see any hands. Any questions online?
I don't see any for the moment.
All right. So, Spiros, we'll let you go to bed. Thank you very much for your presentation.
Thank you very much for having me.
Let's thank the speaker again, please.
Have a good one.